spectroscopic terms. Alright? From our previous knowledge, we are all aware of electronic configuration. Like electronic configuration of which we have quantum numbers. We have the principal, we have the subsidiary, we have the magnetic, we have the spin quantum number. This is an offshoot. These spectroscopic terms is an offshoot from the quantum numbers. In fact, spectroscopic terms really gives us, the behavior, the position of electrons within orbitals. If we look at principal quantum number, it's going to tell us about the energy level of, of an atom. Subsidiary, the shape, magnetic, the spatial orientation, alright, and so on and so forth. But for these spectroscopic terms or free ion terms, it is actually going to tell us much more information than all of these things. However, like I said, it is an offshoot of quantum numbers. What that simply means is that, for instance, you have in subsidiary quantum number, which is represented by L, you have S, P, D, F. DF, right? In spectroscopic terms, instead of small letter S, they are represented as S, P, D, F. The basic difference is that they are in capital case. You understand? And these ones are in lower case. These ones are in upper case. Now spectroscopic terms. Alright? Spectroscopic terms. They are a set of quantum numbers describing the total electronic states. They are a set of quantum numbers, like I said, describing the total electronic states of atoms, ions, and molecules. Now, for instance, you have a P2 example. E.g. find the spectroscopic terms. Find the spectroscopic terms of carbon 1s2, 2s2, 2p2. In O-level chemistry, you're going to be told, write the electronic configuration of carbon. But you are now in an advanced level. In fact, this topic is a request from my postgraduate students. Alright, so it's an advanced chemistry. Alright, so this is a caveat. It's advanced. Alright, so it's not a sin or it's not needed for those at the lower echelon. Now, find the spectroscopic terms, or we call it free ion terms for metals, of this configuration. What you are interested in, basically, you are interested in the last, actually, it is the last configuration that will give us the atomic, the group number of the atom, and what? And the period of the atom. It is the same last configuration that will give us the spectroscopic terms. How do we apply it? Number one, you know this. Okay? Number two, you say it is a P2, right? If it is a P2, we are going to be finding the microstates table. This microstates table will give us the number of possible ways these electrons can be filled in the orbital. Like I told you, I give you an example. In this case now, we can tell that this carbon has 6 electrons. We can also tell that they are having 2 shells. Alright? We can tell that they are having 2 shells. Alright? Isn't it? But beyond that level, advanced chemistry tells us that this electron, the position, the possible position where you can find this electron is more than this. It's not just an imaginary place. There are specific places. For instance, you have a 3-bedroom flat. The bedrooms are meant to be slept in. Alright? The same thing. The microstates, the positions, are the places where you can find the electrons. So this is what describes those positions. Alright? That is to say, if you bombard a molecule with a spectrum, anywhere the electron is going to, the electron can either fall in any of these positions that we are going to be deriving from this microstate table. Now, how do we get the microstate table? Like I said earlier, the microstate table is giving us the number of positions where we can find electrons. There is a formula for it. The formula is N combination R. When we were in undergraduates, we were taught mathematics, and most times say, what are we using? Factorial, combination, permutation. This is one of its applications. Alright? Now, N combination R, where N is the total number of electrons the orbital can take. In this case, this is a p orbital. The maximum number of electrons a p orbital can take is 6. So N is equal to 6. Alright? R is the number of available electrons. Number of available electrons. In this case, we're having 2 electrons. We're having 2 electrons. Now, to apply this, the number of ways we can arrange these 2 electrons. We're going to have 6 combination 2, and that is 6 factorial all over 6 minus 2. Alright? Factorial 2 factorial, because this guy is n factorial over n minus r factorial r factorial. Our n is 6, our r is 2. So, to get that, we have 6 times 5 times 4 times 3 times 2 times 1 all over 6 minus 2, that's 4 factorial, times 2 times 1 multiplied by 2 times 1. We all know what n factorial means. Or for instance, 6 factorial is that you multiply 6 in a descending order with the numbers below it. 5, 4, 3, 2, 1. And you know what 4 factorial means? 4 times all the numbers below it. So, invariably, to simplify this cancels out. So you have 30 all over 2. That is 15. Alright? That means that we have 15 ways in which we can arrange the electrons, the 2 electrons. We have 15 ways in which we can arrange